Dear students, today we will discuss the very important characteristics of the transmission line, that is the characteristic impedance. In your university exam, you may be asked for the derivation of the characteristic impedance, what is characteristic impedance, and along with that some numerical based upon the formulas for the lossy and lossless line can be asked. So be careful while learning this. Let us consider that what is transmission line. Here in this diagram you can see that if there is a certain signal which is a physical quantity, in that case that physical quantity is first fed to the transducer. As you know, the transducer is the device which converts the physical quantity into its analogous electrical signal. That analogous electrical signal is needed to be transferred over certain distance. So if we have certain source and the destination, there must be some connectivity between the source and destination in order to transfer the signal from one end to the another end, and that can be achieved with the help of device called as transmission line. So you can say that transmission line is nothing but a medium which transmits the signal from one end to the another end, or which makes the signal available from source to the destination. So we have one source and the destination. So here we can see that the source is generally known as the generator and the destination is known as the load. So we will use these terminologies only in the transmission line, that is the generator and the load, as we can see on the figure. Then the equivalent circuit of the transmission line. The equivalent circuit of the transmission line uh, the equivalent circuit of the transmission line consists of the series resistance, series inductance, shunt capacitance, and the shunt conductance. So here you have the R, L, G, and C. All these parameters are the per unit length parameters. We will see why they are there and how these distributed elements makes up the equivalent circuit of the transmission line. Let us discuss every uh, component or the distributed component of the given equivalent circuit individually. So as we know that there is a uniform transmission line available with us, so it will have the distributed circuit and will have the four components, that is resistance, inductance, capacitance, and the conductance. So the first is resistance. If there is any conductor and if it has particular length and some cross sectional area, in that case we can find the resistance as rho L by A. So if there is a length and there is a area to the connector, in that case it will have certain amount of resistance. If this resistance is per unit length, it will be given as ohm per meter. The unit will be ohm per meter, and this particular resistance is always connected in the series of the equivalent circuit of the transmission line. And the most important thing is that it causes the voltage decay along the transmission line. So as we traverse across the transmission line, the voltage will be decaying because of this resistance. That means it causes certain amount of loss. So if the loss is there, resistance will be there. Then the inductance. The inductance, as we know that if the conducting material is made up of magnetic material and it has certain amount of length and the cross sectional area, it will definitely possess some inductance, and that inductance will be then dependent upon the length and the area, cross sectional area of the material. So the inductance is, it is always distributed over the complete transmission line and it is in the series. Now inductance, it is because of the current flowing through the transmission line, and as it is unit per length, per unit length will have the unit of Henry per meter. So all these characteristics R, L, G and C will be per unit length characters only. Then we have the another characteristics, that is the conductance. The conductance, it is denoted by capital G, and we know that if there is a conductor, in that case the parallel wire conductor, the between two parallel wire there is a dielectric, and if this dielectric is not a perfect insulation, in that case there will be some leakage through it, and that leakage current is known as leakage current. Now if we know that there is a shunt between the lines, then in that case the current decay will happen because of this conductance, and therefore we can say that the loss of current is because of this conductance. So whenever there will be the loss of current, the conductance will be there. So the R and G both are causing the losses in the transmission line. Then the capacitance, if the two wires are separated by certain amount of dielectric and there is a distance between these two, in that case there will be certain capacitance. It is definitely there will be a parallel capacitance available in the transmission line, and this is known as the shunt capacitance. It will be between the lines. As it is per unit length, again the unit will be farad per meter. Now we are on to calculate the characteristic impedance of the transmission line. So before going into the derivation of the characteristic impedance of the transmission line, we must first know what is the characteristic impedance of the transmission line. If we consider a transmission line of infinite length, in that case the characteristic impedance of the transmission line is denoted as Z0, and the impedance is measured at the input of this line when the length is infinite. So if we consider that we want to have the maximum power transfer, in that case the input impedance must be exactly equals to the output impedance, and in such a case for the infinite length transmission line, the impedance is measured at the input of the transmission line, and that impedance is known as characteristic impedance of the transmission line. So let us consider the equivalent circuit of the transmission line as seen earlier. Then we have the current is there flowing into the terminal, and as we know that it causes certain amount of change in current, so I of Z plus di. Similarly, if there is a change in resistance, change in voltage, that is V of Z plus dV. R, L, G and C are the components, distributed elements of the equivalent circuit of the transmission line. R and L are in series and G and C are in parallel with each other. So let us first calculate the series impedance for the given circuit. As we are going to calculate the series impedance, we will consider the G and C to be 0 and only consider the R and L in the circuit. In such a case, the equation can be written as the V plus dV minus V plus dV plus V is equals to JWL dZ. This is your inductive capacitor, inductive reactance, and R is your resistance dZ plus I. If we take the dZ common out of this, and minus V plus V gets cancelled, in that case dV divided by dZ is equals to minus R plus j omega L into I. We need to remember this equation, that is dV by dZ is equals to minus R plus j omega L into I. Let us consider this as a equation number 1, which is the series impedance for the given transmission line. Now we calculate the shunt admittance. In such a case, we will consider the change in current from input to output. So the current is changing from I to I plus di. So I minus I plus di is equals to G plus j omega C, that is the capacitive reactance, into dZ into V. So again I minus I gets cancelled, di by dZ is equals to minus G plus j omega C into V. So that is your equation number 2. So first is your series impedance given by equation number 1, and another is your shunt admittance given by equation number 2. So if we consider the equation number 1 again, that is dv by dz is equals to minus r plus j omega l into di. So if we consider if we consider that equation over here and differentiate it with respect to z, in that case d2v by dz square is equals to minus r plus j omega l into di by dz. Now we have the equation number 2 where di by dz is equals to minus g plus j omega c into v. Let us put this value in the above equation. In that case we will get d2v by dz square is equals to r plus j omega l into g plus j omega c. Minus into minus will become plus, and di by dz is equals to v. So you have d2v by dz square. Let us replace this term r plus j omega l into g plus j omega c by gamma square, where gamma is our propagation constant given as under root of r plus j omega l into g plus j omega c. This propagation constant is actually consists of two constants. One is real part, that is alpha, known as attenuation constant, and is given in Napier per meter, whereas the beta, it is the phase shift or the phase constant, which is a complex part, and it is given as radian per meter. So we need to remember this equation, that is d2v by dz square is equals to gamma square into v. Again the alpha is actually the attenuation of the signal due to the resistive losses. If the r is there, alpha will be there, and the beta is the propagation property of the signal wave without any loss. So the alpha is the real part as we have seen, and the beta is the complex part of the decay. So we have the r, l, g and c, which are our primary constants, and the gamma is our secondary constant because we have derived it from the primary constants. Now if we consider that equation number 3 where d2v by dz square is equals to gamma square into v, if we try and solve this differential equation, we will get v of z is equals to a into e raised to power minus gamma z plus b into e raised to power plus gamma z. So we have differentiating this equation with respect to z, we will get dv by dz is equals to minus gamma a into e raised to power minus gamma z plus gamma b into e plus gamma z. Now if we consider this equation and take the gamma common, in that case minus gamma into a raised to power a into e raised to power minus gamma z minus b into e raised to power gamma z. Now if we consider the equation number 1 of our derivation, in that case we can put the value of dv by dz as r into j plus omega l into I, and therefore we can rearrange this equation as dv by dz is replaced by r plus j omega l into I. So I is equals to gamma upon r plus j omega l. The minus was there in the equation number 1 and the minus is here in the this equation number 5. So minus minus plus. So gamma upon r plus j omega l into a e raised to power minus gamma z minus b e raised to power gamma z. So here if we consider the value of gamma again, putting the value of gamma over here, in that case the gamma value was under root of g plus j omega c into r plus j omega l. We get the another equation, that is I equals to under root of g plus j omega c into r plus j omega l. So we know that this is nothing but your v of z. So I into something is into v is nothing but I into 1 upon z or you can say that I into admittance, sorry, I is equals to admittance into V. So 1 upon Z0, therefore we can say that the Z0 from this equation will be R plus j omega L upon G plus j omega C. This Z0, it does not depends upon the length of the transmission line, because it depends having the parameters R, L, G and C. All these are the per unit length characteristics. We need not to calculate the values for the whole length of the transmission line. So this is the characteristic impedance for the transmission line which is having the losses, that is for lossy transmission line. Now if we consider the dependency of the Z0 on the parameters, in that case it depends upon the metal of the conductor, which particular metal is being used to form the conductor, dielectric material being used, and the geometry or the cross sectional area of the transmission line where R, L and G, C will be affected. So for the transmission line which is lossy, we have calculated Z0 is equals to under root of R plus j omega L into G plus j omega C, which is a complex quantity. For lossless transmission line, as we have seen, the resistive losses are 0 and the conductance losses are also 0. There is no leakage, and in that case the Z0 is equals to under root of L by C, because R and G is 0. So in such a case, gamma will be equals to alpha plus j beta, that is under root of R and G will be 0. Therefore, under root of j omega L into j omega C, j omega into j omega square, it will be taken common like this, j omega and under root of L C. So from this we can calculate the alpha is equals to 0 and beta is equals to omega into under root of LC. These are the equations for the lossless transmission line, where the attenuation constant alpha is 0 and beta is the linear function of the frequency. So that's all about the characteristic impedance of the transmission line.